In this segment, we're going to look at the concept of deterministic encryption that often comes up in practice. When I say deterministic encryption system, I mean an encryption system that will always map given message to exactly the same ciphertext. So if we encrypt the same message 3 times, every time we'll get exactly the same ciphertext. So there are no nonsense involved here. Literally, this is just a consistent encryption scheme that will always output the same ciphertext given a particular message. So let's see where this comes up in practice, and in particular I want to show you the case of lookups into an encrypted database. So the settings are, imagine we have a server here that is going to store information inside of an encrypted database. So what it'll store is records, and every record has an index and some data that's stored inside of the record. Now, the first thing the server is going to do is he's going to encrypt this record. So here the record became encrypted, and you notice that the index became encrypted with K1 and the data is encrypted with K2. And then the encrypted record is sent over to the database. And the same thing happens to many records, so that the database overall holds many encrypted records, where again you can imagine that the index is encrypted using the key K1, and then the data in the records is encrypted using the key K2. Now, if encryption is deterministic, the nice thing about that is that at a later time, when the server wants to retrieve a record from the database, all he needs to do is send to the database an encryption of the index that the server is interested in. So here it would send an encryption of the index Alice. That again becomes encrypted, and the resulting ciphertext is identical to the ciphertext that was generated when the record was first written to the database. And the database can then, find a record that has this encrypted index in it, and then send the result back to the server. The nice thing about this is that now the database is completely in the dark as to what data is stored in the database, and it doesn't even know what records are being retrieved by the server, since all it sees are basically requests for encrypted indices. And so this deterministic encryption mechanism lets us do a quick lookup in the database given an encrypted index, and we're guaranteed that because of the deterministic encryption property, that the index is going to become encrypted in exactly the same way as it was when the record was created. And so this should be disturbing to many of you, because we previously said that deterministic encryption simply cannot be chosen plaintext secure. The problem is that an attacker can look at different ciphertexts, and if he sees the same ciphertext twice, he knows that the underlying encrypted messages must also be the same. So in other words, by looking at ciphertext, he can learn something about the corresponding plaintext, because every time he sees the same ciphertext twice, he knows that the underlying messages are equal. In practice, this leads to significant attacks, and particularly when the message space is small. For example, if we're transmitting single bytes across the network, such as keystrokes that are being transmitted one keystroke at a time, then in fact an attacker can simply build a dictionary of all possible ciphertexts. If it's only single bytes, then there will only be 256 possible ciphertexts. And then simply by learning what the decryptions of those ciphertexts are, he can actually figure out all future ciphertexts simply by looking them up in this dictionary. And so there are many cases where the message space is small, where this deterministic encryption simply is insecure. Now concretely, in the case of an encrypted database, what the attacker would see is if there are 2 records that happen to have the same ciphertext in the index position, then now he knows that those 2 records correspond to the same index. So again, even though he doesn't know what the index is, he learned something about the corresponding plaintexts. I wanted to briefly remind you that formally we say that deterministic encryption cannot be CPA secure by describing an adversary that wins the CPA game, the chosen plaintext attack game. And let me quickly remind you how that works. The game starts by the adversary sending 2 messages, M0 and M0, and remember that in this game, the adversary is always going to be given the encryption of the left message or the encryption of the right message. In this case, since he used the same message in both cases, both on the left and on the right, he's simply going to get the encryption of the message M0. In the next step, he's going to send the messages M0, M1, and now he's either going to get the encryption of M0 or the encryption of M1, and his goal is to tell which one he got. But because the encryption is deterministic, this is very easy for him to do. All he has to do is just test whether C is equal to C0. And if C is equal to C0, then he knows that he got the encryption of M0. If C is not equal to C0, he knows that he got the encryption of M1. So he can output 0 if C is equal to C0 and output 1 if C is not equal to C0. And his advantage in this particular game would be 1. So it would be as high an advantage as possible, which means that the attacker completely defeats chosen plaintext security. Okay, so this is just a formal way of saying that the attacker basically learns more information about the plaintext than he should. So the question is, what do we do? And it turns out the solution is basically to restrict the type of messages that can be encrypted under a single key. And so the idea is to say that suppose the encryptor never ever ever encrypts the same message under a single key. In other words, the message key pair is always different and never repeats. So that for every single encryption, either the message changes or the key changes, or both change. But it can't be that we encrypt the same message twice under the same key. So why would this ever happen? Well, it turns out there are very natural cases where this happens. For example, if the messages happen to be random, say the encryptor is encrypting keys, and those keys, say are 128-bit keys, so they'll never actually, with very high probability, they'll never repeat. In this case, when we're encrypting keys, in fact, it's very likely that all the messages that are encrypted under one master key are always distinct, because, again, these keys are very unlikely to ever repeat. The other reason why messages would never repeat is simply because of some structure in the message space. For example, if all we're encrypting are unique user IDs, so imagine in the database example, the index corresponds to a unique user ID, and if there's exactly one record in the database for each user, that says that every encrypted record basically contains an encrypted index where the index is distinct for all records in the database. Okay, so these are two reasons why messages might never repeat, and this is a fairly reasonable thing that actually does happen quite often in practice. So now, if the messages never repeat, now maybe we can actually define security and actually give constructions that satisfy our definitions. So this motivates the concept of deterministic chosen plaintext attacks, and let me explain what they mean. So as usual, we have a cipher defined as an encryption and a decryption algorithm. So we have a key space, a message space, and a ciphertext space. And we're going to define security just as normal using two experiments, experiment 0 and experiment 1. And the game actually looks very similar. It's almost an identical game to the standard chosen plaintext attack game, where basically the attacker issues queries. So you can see these queries consist of pairs of messages, M0 and M1. As usual, they have to be the same length. And for each query, the attacker either gets the encryption of M0 or the encryption of M1, and the attacker can do this again and again. He can do this Q times, and at the end of the game, he's supposed to say whether he got the encryptions of the left messages or the encryptions of the right messages. So this is the standard chosen plaintext attack game, but now there's one extra caveat, which is to say that if the bit is equal to 0, if B is equal to 0, in other words, the attacker always sees the encryption of the left messages, then it so happens that the left messages must all be distinct. In other words, he will never get to see the encryption of the same message twice because these left messages are always distinct. So if the bit B is equal to 0, again, he'll never see the same message encrypted under the same key because, again, these 0 messages, M10 to MQ0, are all distinct. Similarly, we require that all the 1 messages are also distinct, and so that, again, if bit B happens to be equal to 1, the attacker will never see 2 messages encrypted under the same key. Okay, so this requirement that all these messages are distinct, and similarly all these Q messages are distinct, basically captures this use case that the encryptor will never encrypt the same message multiple times using one particular key. And as a result, the attacker simply can't ask for the encryption of the same message multiple times using the same key. Now I should point out, if you go back to the original attack here, so here we go back to our CPA attack on deterministic encryption, you notice that here, in fact, this is not a deterministic CPA game because here the attacker did ask for the same message M0 to be encrypted twice. So in fact, this attack would be an illegal attack under the deterministic CPA game. And by ruling out this attack, we actually make it plausible that we might be able to give constructions that are deterministic CPA secure. And so as usual, we say if the adversary cannot distinguish experiment 0 when he's given the encryption of the left messages from experiment 1 when he's given the encryption of the right messages, then the scheme is semantically secure under a deterministic CPA attack. Okay, so as usual, we ask for what's the probability that the adversary outputs 1 in experiment 0, what's the probability that he outputs 1 in experiment 1, and if these probabilities are close, then his advantage in attacking the scheme is negligible, and if that's true for all efficient adversaries, then we say that the scheme is semantically secure under a deterministic CPA attack. So the first thing I want to do is show you the cipher block chaining with a fixed IV, in fact, is not deterministic CPA secure. And this is a common mistake that's used in practice. There are many products that should be using a cipher that's deterministic CPA secure, but instead they just use CBC with a fixed IV and assume that that's a secure mechanism. And in fact, it's not, and I want to show you why. So suppose we have a PRP that happens to operate on n-bit blocks, and we're going to use this PRP in CBC mode. So, if there are 5 blocks in the message, then this PRPE will be called 5 times to encrypt each one of those blocks. Okay, so here's how the attack's going to work. Well, the first thing the adversary is going to do is he's going to ask for the encryption of the message 0 and 1n. In other words, the first block is all zeros and the second block is all ones. So the left message is equal to the right message here, which means that he just wants the encryption of this 0 and 1 to the n message. So let's see what the ciphertext looks like. Well, for completeness, I'm going to write the IV, the fixed IV, as the first element in the ciphertext. And if you think about how CBC works, the second element in the ciphertext is going to be basically the encryption of the IV XOR the first block of the message. Well, in our case, the first block of the message is all zeros, so really all we're encrypting is just a fixed IV. So the second block of the ciphertext is simply going to be the encryption of this fixed IV. So next what the adversary is going to do is now he's going to output 2 messages that are a single block. So the first message is going to be, the message on the left is going to be the all zeros block, and the message on the right is going to be all ones block. So observe that this is a valid query because messages on the left are all distinct, and the messages on the right are also all distinct. So these are all valid deterministic CPA queries. Now, what does the attacker get in response? Well, what he'll get in response is the following. If he gets the encryption of the message on the left, then, well, what's the encryption of the one block message 0 to the n? It's simply the encryption of the fixed IV, just as we saw before. However, if he's getting the encryption of the message on the right, well, that's going to be the encryption of 1 XOR the fixed IV. That's just the definition of CBC encryption. And now you can see basically how the attack is going to proceed. You notice if, here, I'll use a different color here. You notice if these 2 blocks happen to be the same, then we know that he received the encryption of the message on the left. In other words, B is equal to 0. If they're not the same, then he knows that B is equal to 1. Okay, so he's going to output 0 if, C of 1, which is this block, is equal to C1 of 1, which is this block, and he's going to output 1 otherwise. So this basically shows that CBC with a fixed IV is completely insecure. Basically, the first block can be very easily attacked, and in fact, if the messages are short, you can again build dictionaries and completely break systems that kind of use CBC with a fixed IV, hoping that it's going to be deterministic CPA secure. So don't do that. We're actually going to see secure deterministic CPA constructions in the next segment. So I'll say it one more time. If you need to encrypt a database index in a consistent manner, don't use CBC with a fixed IV to do it. Use the schemes that I'm going to show you in the next segment. And so let me ask you the same question about counter mode with a fixed IV. Is this going to be a deterministic CPA secure system or not? And here I'm reminding you what counter mode with a fixed IV is. Basically, we concatenate the fixed IV plus 1, fixed IV plus L. We encrypt all these counters, we concatenate the results, we encrypt the message to get the ciphertext. So do you think this is going to be deterministic CPA secure? So I hope everybody said no, because basically this is a one-time pad encryption, and if we use this one-time pad to encrypt distinct messages, basically we'll be getting a two-time pad. And to see it more precisely, here I wrote down the deterministic CPA game. So you notice what the attacker would do is he would start off by asking for the encryption of the message M. So he would get here the message M XOR the encryption of the fixed IV. And then he's going to ask for some 2 distinct messages, M0 and M1, that's different from M. So M, M0, and M1 are all 3 are distinct messages. And then what he'll get is the encryption of MB, and now he can simply mount a standard kind of 2-time pad attack. And if this equality here, if C XOR C prime is equal to M XOR M0, he knows that C prime is the encryption of M0. And otherwise, he knows that it's the encryption of M1. So again, he will completely win this game with advantage, as usual, with advantage equals to 1. Okay, so again, deterministic CPA with a fixed IV is also completely insecure as a deterministic CPA cipher. So don't use any of those schemes. Instead, let's use the schemes that I'm going to describe in the next segment.